area and environment in Inventor Professional, which potentially you might be using this. I personally believe for this project, the Fusion 360 would be sufficient enough, and the shape optimization function there would be sufficient enough. However, I've also provided you with the Inventor just in case you would like to perform some other analysis and some other designs with respect to that as well, especially in your future. It's not as intuitive, in my opinion, as a Fusion, but it's pretty similar. So the first part is, how do you actually go and design your tube, your hollow structural section that we talked about? So the first thing is that you have to go to the modeling side. And the first part is that you go to the 2D sketch. Once you go to the 2D sketch, now you have to decide where is it that you want to lay your foundation? Where is it that you want to lay? With respect to that, you go up and down. And here in Inventor, you have the XZ plane at the very bottom, essentially. That's how it's shown. So we're going to go ahead and do it in that way too. Then what you need to do is there's various different types of, let's say, simple, obvious. Anyone who has worked with AutoCAD, which I'm quite certain everyone has, knows these types of commands. You basically go to the rectangle, and then here, for instance, the units are in inches. Imagine if I want to change it to something else. You go to the tool section, and you go to document settings. Then you go to units, and then you change it there to, let's say, millimeter, centimeter, whatever it is that you want to change. You apply and then close it. And then we go back to our sketch. We basically start from the origin, and we want to have a rectangle that is around it. So I said that that rectangle is going to be approximately, the dimensions are about, let's say, 75 centimeter if we have the inner dimensions of that column. That means that if you have 2 centimeters from each side, then it's going to be 79 centimeter or 790 millimeters. Okay, you could have also done this in centimeters. There's no problem. So you go basically, and then what you need to do is here, you need to go inside of it and then basically do another one that is smaller than that, that is going to be exactly the surrounding of your column. So we assume that the column is going to be 75 centimeters. Then the outer layer is going to be 79. So the inner layer is going to be 75. So how I've done it is the simplest and the crudest way possible. I go from each and every from one side of the rectangle, go 20 millimeters or 2 centimeters to the left and 2 centimeters bottom. And then the same with the other side as well. And I just go and attach these two together. You would have been able to also use the scale command for this, but I'm just using the simplest way possible to kind of give you some ideas with respect to that. And you go ahead and you essentially go and delete the extra lines there. And the software is quite intuitive in this way, meaning that now that you go and you say finish sketch, what it ends up doing is that it understands that there's a particular type of surface there that is created between these two rectangles, essentially. What you do is we're going to be using the extrude command. So you can have various different types of surfaces. We can do the internal one or the external one, which is essentially what we want to be able to extrude up and create that tube, or what we call a hollow structural section. You do that, and then it gives you the option to basically specify how long this is or what the height is going to be. So here I did 4,000 millimeter, which is 4 meters. And that is more or less the heights that you would be expecting from this particular element here as well. Once you perform that, then it's always customary to also, for these types of analysis, to also create, like, let's say, some sort of small base underneath to provide you with the option of being able to essentially connect it together in a fixed way, that is also, again, our ideal assumption there. So what I'm going to do is, again, underneath this whole thing, I'm going to have another 2 centimeter rectangle underneath. So again, I go to the sketch, When I go to the sketch, it says on which surface. You have to rotate it and find the bottom part. Again, I do 2 centimeter, 2 centimeter up from one side, and then from the bottom parts, again, I do the exact same thing as well. Again, this is a crude way of doing it. There's much more sophisticated way of doing this as well, but this is the simplest that would work in your assignment as well. Then what you want to do is you want to have this rectangle. You go from one section to the top parts there, and then you have that rectangle there as well. And then you go and basically delete that extra bits that exists there as well between them. So once you select that, then again you can do extrude. Then you essentially go and say, let's say we want to do it 20 or let's say 50 millimeters or 5 centimeters down, or in this case I did 40. And this is basically how it is. This is mostly, I put it there so that not necessarily that it's going to be, but the assumption of the fact that there's a plate underneath and there's going to be some clear constraints that are making it fixed so that we can perform the analysis properly. This is not a part of your project where you also think about the attachment of this new material to the concrete on the outside there. However, I believe this is the ideal circumstance that you can expect at this situation. Okay, so what has happened is essentially that we've now modeled this now a tube. Let's go ahead and see how we can perform, let's say, the generative, the topology optimization setup and simulation. So what we do is, as you saw, we went basically to the Environments tab, and then we clicked on Inventor Nastran. So this Inventor Nastran is has the ability for you to go, and it claims that it provides you with some good design criteria that you can specify in the beginning to be able to perform that as well. But in order for you to be able to do the topology optimization, you need to go and find out basically plug in the mechanical properties and the properties of your material there. From this, of course, the generic material has very, very low elastic, capabilities. You saw the Young's modulus were very, very small. So it's going to deflect significantly. What we have to do is we have to basically select the material that we want. Let's say here you want to do concrete. You could also do plastic. Let's say the polycarbonate that is typically used for a bit more high strength and good ductility, with some of these 3D printers that are able to go a bit higher in the temperature, let's say around 300 degrees of centigrade. And then from that, you basically click OK, and then it updates your material properties that you have. Once you have that, then you have to also create a mesh model for that. So with that, you can go to the mesh settings, and this is exactly where you can increase or decrease your mesh size as well. So here it's saying, element size in terms of millimeters, whether you want to do it finer or coarser. And of course, if you do it coarser, it's going to take much less time, but the accuracy due to the linearized or in this case, parabolic approximation here is going to be more or less. But then when you click OK, this is going to be how it is. You can see it's very, very large. That means that we're not expecting the topology to actually provide a very, very good result in that sense. And then here we have essentially, if we increase that and make it a bit finer, you have that. So the result is going to change if you have a different mesh size. Then the other side is to provide it with the load constraints. You can go there and basically right click and say new. You can call it a particular name, and then you can provide it with what type of load it actually is. It could be a distributed, but pressure load is the best. It's assuming that you have essentially another surface on the top that is pressuring it downwards. And The units of that is megapascals, and megapascals is Newton by square millimeters, if I'm not mistaken. So that's going to be your results. And if you say by means of the 79 and the 75, basically the area and then the 100 kilonewtons, if you divide them, it's going to be approximately 1.7 megapascals. So you provide that. Then the next part is that you have to provide constraint, and we're going to do a fix there. Once you do the fix, you see the Tx, Ty, Tz, and the rotations are all fixed. And then you go and basically from the left side, select all of those items from the bottom, and then you click OK, and you ensure that it is fixed. This is so that we're basically saying that this is completely fixed, so nothing is changing there. And then you have essentially your supports there. Then what is interesting about this is that you can provide basically design criteria there by means of the parameters. So here you have the design optimization by means of the topology optimization, and you see the top TOP TGen. If you enable that, this will provide you with the option to have topology optimization by means of different design criteria. So if you go to essentially, and then by means of thresholds, so you have the compliance, you have the stress, you have the displacement based, and then from that so compliances, they have some particular objective function that they define. It could be by means of the stress. It could be designing by means of the displacement to ensure that the displacement is not more than a particular item. And then the second part is the additive manufacturing side of it. You can say, okay, I want it to be with only symmetrical, meaning that dependence upon how it is, I want my design to be symmetrical from all sides, or by means of a particular, let's say, plane. Or you can say that I want it to be optimized by means of additive manufacturing, meaning that the overhang angles, and what the overhang angles essentially mean is that you have, let's say, an item that is going like this. Okay, it's completely hollow, and what ends up happening is, if you're additive manufacturing, we're going to talk about that when we get there. If it goes like that, then it's going to collapse. There's not going to be some support. So then you have to provide the support structure there as well, which is not really required if you can minimize that as much as possible. So with the optimization there, instead of having these curves, then you might have, let's say, much larger curves, or much let's say, sharper, that is more or less more than, let's say, 45 degrees angle. And that would provide you with a very, very good opportunity for you to essentially get that sorted. So then you have essentially all of those components and everything. Here, I'm just going to run a stress analysis. I'm not going to go too much into detail about the topology optimization and those criteria, each and every one of them. If you click on it, it takes you to a different stage, and then it gives you an idea of what each and every one of those aspects means. The last part where you have to take on the consideration is with respect to the reference coordinate system that you have to provide. So this here, you need to provide, let's say, a point on the origin, a point on the XZ, and a point on the Z. So here I'm just going to basically follow suit and do what you have here in terms of the XYZ. However, you can change that as well, and then have it with respect to that. And in that case, then you have to make sure in that your parameters, let's say, the symmetry that you're asking with respect to 2 or 3 or more essentially planes that you've defined. If you want those symmetries, then you have to go and check it and ensure that those symmetries are proper. Okay. So here I'm just going to do a run with respect to regular stress analysis, and then you save your results and then take it from there. However, you're more than able to perform whatever you want to perform here as well, and then essentially take it from there. And then at the end, once it does its nice, little solver from the Nastran solver that it uses, you would be able to then have the ability to basically see what the stress is, what the strain is, and and so on and so forth, the von Mises stress, the displacement, and all of these items there. Again, the simulations are simple, and then you have the idealizations there as well. And then at the end, you have, let's say, what you have here with respect to, the design iterations and so on and so forth. And then you have where basically you have larger stress, where you have smaller stress, and then you can take it from there and see how it is. In some other cases, when you basically change the symmetry, it's not as symmetrical in that sense in terms of the final result. So these are all things that we can essentially take under consideration and see how it is. This is, for instance, the displacement profile. You can see and at least have a judgment and understanding of how it is. In this particular situation, it's almost 3 millimeters that is going to be displacing by means of some sort of reduction or whatever has been modeled. So we have to take that under consideration as well. You can also change the options there and see what we would have to do, let's say by means of stress. Then we can specify minimum and maximum.